Recording in progress.
Okay, it started recording.
Okay, so today we have quite some work. Actually, today it's a nice tutorial, but I hope we are going to do work which will help you understand, because one of the problems is that we get bogged down in the details, in technical details. Game theory is not like a very technical topic, but it is. In this course, it is. But actually, techniques help you sometimes. So let's start with the price finding exercises. We made the first 3 parts, and let's make the last 3 parts. It's very quick. I think it's still a good idea to make it. No, one note. I, by the way, wrote you that you also are welcome to watch our Gardner's lecture on that last topic. But again, as I emphasize, it's just if you want. It's absolutely not a part of the material of the course. I'm sure he explains that much better than I do, because he's a great lecturer and because he actually did that himself. But still, I'm not requiring you to do that.
Yes.
Now let's go further.
Professor, could you share your screen also?
Yes. I'm just open the. Do you see the screen?
Yes.
Great. One second, I need to connect the tablet. Okay, let's hope it doesn't give us that treatment it did on the previous tutorial. So it's fine. Problem 1. Good. Actually, that's a continuation from the previous tutorial. So that's did till including 3. You see, right? You see my screen?
Yes.
You hear me. Good. Thank you. Did 3 as the previous tutorial. Again, if I go too quickly or something, let me know, because I think that since I don't see your faces, it's harder for me to estimate how quick I need to go. And of course, if I go too slowly, that's also fine if you tell me. I mean, I just don't need to explain stuff you understand. So I remind you that we had 2 options to calculate. What we need to do is to calculate the prices in this mechanism, and then to calculate what are the allocations. And we said that we can just calculate first the prices and then using them calculate the allocations, or just calculate the allocations separately. So what we said is that VI, the sum of the okay, so every player I gets VI divided by the mu, which is the price. That's what player I gets. So how much she's able to invest, divided by what is the price. The sum of all the players from 1 to capital R, for example, is equal. Eventually, it has to be equal. The price is set so that it's equal to C, the total divided amount of the goods. So then the price is equal excuse me, to the sum of all the W's divided by C. And it's also intuitive. So the price is basically what are the total number of what players are offering for that. Divide the more the offer, of course, the higher the price, and the less, or let's say the more we have to share, the lower the price. Now that's one. And then we said that one of the ways to divide then what player I or Ri, whatever I gets, let's say R, is basically, as I said, what we said before, right? The price, what she invests divided by the price, and then we can just substitute the price, and that's going to be what she invests divided by it's R, it's not I. And what she invests divided by the total investment of the others. I just substitute this expression for the price and use price. I apologize for this notation. It's from the book. I don't remember why they don't use P. Probably they already ascribe some other meaning for that to that letter. Anyway, so I equal to 1 till R and CS. So that's, and we also see that just the proportional allocation. So player R gets the proportion of her bit relative to the sum of the other bits of this total amount we share. So we don't need to calculate the price explicitly to calculate D. We still anyway calculate the price in this exercise, so it's like it's free for us, free in the sense that it does not require extra effort, but we don't have to. So let's move to the solving. So we now solve part 4. So what is the price? The price is the sum of the bits divided by C. So the price is the sum of the bits. So 1 plus 2 plus 3 divided by C. C in this case is 10. So divided by this 10, which is 6 divided by 10, which is 0.6. And then, or maybe I should also actually leave it like as a normal fraction. 3 divided by 5. I guess it will be easier for calculating. And then we can immediately say that because of that, the player 1 gets what she gives, which is 1 divided by the price by 3 over 5, so it's 5 over 3. Player 2 gets what she gives divided by the price, which is 2 divided by 3 over 5. So that's going to be 10 over 3. And player 3 gets what she gives divided by the price. Oh, I've picked the wrong 2. Player 3 gets what she gives divided by the price, which is 3 divided by the 3, 5, which is 15 over 3, which is 5. Don't have to simplify it even, but it's 5. Good. Let's say the next exercise we're going to calculate these differently, just for practice. So the next exercise is what is the price? So tell me, what is the price here?
10 divided by 5.
10 divided by 5. Why 10?
Oh,
right.
No. So, no, it's 0 plus 2 plus 3 divided by 10. My bad.
Yeah, exactly. So, well, basically, I think you understand. It's just a question of numbers, and here we all can always get confused. So it's 5 over 10. It's half, and then we can either calculate these as before, but let's now calculate for the sake of exercise just from the proportional value of the bits. So then now we can. By the way, there was a mistake, a typo. I would how shall I say it? A pen slip in the previous exercise, we did something which was not exactly what should be done. We said one thing and I wrote another thing. Let me, before I forget, let me just tell it to you. So that's the what I wrote here. So you see at some point, the solution of part 2, I will
Yes.
calculate the price, and then we start calculating the allocations. Now, the allocation to the second player is what she gives, which is 2, divided by the sum of allocations, which is 1 plus 2, times, oh no, sorry, I think it's, no, yeah. Okay, that was the first part. So the allocation of the second player is 2. Let's see what was that. So it's the first part. The second allocation to the second player was 2 divided by the sum of the allocations, 1 plus 2. I'm talking about the first part. And instead of that, I wrote 1 plus 3. I'm just making it clear that, and of course, times the total amount of resource, which was, where is it? Was 1. Just was a pen slip, so just that you know. I hope that you don't get confused, especially you who attended the tutorial, but still. Good. Go back. Let's go back. Now, so the allocation player 1 obtains is, okay. And now I have a technical problem again. The allocation player 1 obtains is what she obtains 0 because her bid is 0. So her bid is of course 0. So D1 is 0 divided by something is 0. Something not 0 is 0. Something greater than 0. D2 is, how much is D2? We are back on question 5. How much is D2?
2 divided by half, so 4.
2 divided by, well, half, 0 plus 2 plus 3. Times 10, of course. It should be times 10. Anything. So 2 divided by, well, the sum of the bits.
5 times 10.
Repeat, please. I didn't hear you.
2 divided by 2 plus 3 whole multiplied by 10.
Yes, exactly. So 2 divided by, and that is just 2 divided by 5 multiplied by 10, it's 4. Yeah, and this 3 is equal to 3 divided by 0 plus 2 plus 3 multiplied by 10. That is, we can of course also, since we in this mechanism we don't throw away anything, we can also just tell that it's 10 minus everything we have already allocated, which is 10 minus 0 minus 4, so it's 6. That's yet another way to see what happens here. So it's 3 divided by 5 times 10, it's 6. Okay. Also 10 minus 0 minus 4. Good. The last part, and then we go to the more challenging exercises. So, what is the price here? So, price is the sum of the W's divided by the resource, which is, how much is it?
Resource is 10.
Yes, 0. Okay. Can you please repeat? I'm not sure.
The resource is 10. Right?
Yes, but I'm asking now simply to tell me the whole thing. So how much is the sum of the
5 divided by 10, so price is half, 1/2.
0 plus 0 plus, yeah, that's good to tell 0 because I just want to see how it's done, not of course not the actual numbers. So it's half, that's the price, and now we can calculate D1 is, let's calculate using the price. So D1 is simply how much player 1 tell, it's 0. D1 is 0. D2 is 0. Now D3 has to be everything. but we can also calculate it. It's simply 5. Either we can calculate it using for the price, so it's like 5 divided by half, which is 10, or we can tell that it's simply it's simply 5 divided by the sum, which is also 5, or that what is left. So I hope you're already familiar with all those things. So let's move, unless you have some questions.
No.
Okay, then let's move to the second exercise. That's something we spoke about: price taking and price anticipating mechanism. And because again of this calculus confusion, it was quite hard maybe to get the intuition. I want now to. So we said that this is basically it's a different thing in general. So I wanted to find an example of a competitive equilibrium. So equilibrium when you have price taking users, that is not Nash. So that is not an equilibrium in the game where you have this price anticipating users, and the other way around, a Nash equilibrium which is not competitive. So do you have any idea, any suggestions? I found a very simple example. It does work. I'm not sure it's kind of very illustrative, but it does work. Let me see what we plan to do also. Yeah. Okay. Yeah. So my apologies. Yeah, I was wandered away. So what about this exercise? Any suggestions? I should remind you. Let's look at the book. So for the sake of change, let's look at the book, not at because the lectures you have anyway. The book, how the book defines. So the book defines a competitive equilibrium that every player, given that you have a price which is determined by indeed the bits and the total amount of the resource. You see the book, right? I'm now.
Yes.
So given that price, but now forget that it's changed. It has to be equal to that. But now you need to make sure that you cannot increase what you have, which is this, by changing W when the price is assumed to be constant. That's the competitive equilibrium. Now, the Nash equilibrium is indeed simply the maximization of the same expression.
Yes.
But then you take into account that you need to maximize, you need to take into account the price depends on what you are doing. So you kind of, in the competitive equilibrium, you basically minimize the amount of degrees of freedom, you minimize the options to deviate. Or let's say so, my apologies. When you deviate, you don't consider that the price changes. It would, of course, in reality, but you ask, can you profitably deviate if the price didn't change? That's kind of the idea. Okay, so I just was thinking of a very simple function. And it seems to work, but again, I got a bit confused because of the technical part, but it eventually worked. Let's try to do what I did, and if you don't find any mistakes, it will be fine. So let's consider two players, n equals to 2. The size of the resource is 1, of course, and let the function be the same. So let the value of player 1 be equal to the value of player 2 be the identity function, just x. Pay attention, that's convex and concave, but it's not strictly concave. It's fine, we don't have to assume that, but maybe it will be easier if we assume something strictly concave, like x squared. And we also assume the same function for both players. So it should be fine. Well, I mean, it should be. It's not promised to us that there is an equilibrium which is competitive and not Nash or the other way around, but it might be, there is no reason for it not to be the case. And if I haven't made a mistake, that is fine, but I'm just making clear how extremely simple the example I'm taking is. It does satisfy all the requirements of the assumption 1, which is that the utility functions are concave,
Yes.
strictly increasing, continuous, and of course continuously differentiable, just a linear
Yes.
function. Did you ask something?
No, yeah, I was just like agreeing. Yes.
So let's see. The right derivative at 0 is finite, of course. It's 1. That any derivative at any place here is 1. So let's take a look what happens here. So let's take a look, and I start with asking what is the equilibrium? What is actually the Nash equilibrium here? So I look at this function and I write this function. So QR, what is the Nash equilibrium? QR of WR is equal to VR of what you obtain from the mechanism, which is WR divided by W1 plus W2. In this case, that's the whole sum, times C. I'm basically writing this expression. Stop me if you at some point feel that I'm doing something you don't understand or don't agree with. So that is the QR. And now I want to, of course, VR is simply the identity function, so that can be rewritten as WR and C is simply 1. So it can be written as WR divided by W1 plus W2 minus W1 or WR. I write it for a general user. Let me make it less ugly. WR minus W, yes. Now let me take a derivative of that thing. So the derivative of Q R by, of course, by WR is the following thing. First of all, well, simply the simple rules of deviation of derivation, not deviation but derivation, times 1 that's the derivative, and that's equal to W. So let's assume that you're talking about player 1. So let's, because I want to, or I can distill 1 and J, but I think it's fine if we assume that player 1 that first RB1, it means player 1. So let's see how that player optimizes, and then the derivative is going to be W2 divided by the sum squared minus 1. That's the derivative. That's what we want to be 0, to have this possible extremum. And that's 0 if and only if W2 is equal to W1 plus W2 squared. Now, since we can do the same for player 2.
Plus 1, right?
No. We moved R1 to the right-hand side.
Oh, yes.
Multiplied by W1 plus W2 squared.
Yes.
Agree?
Yes.
Okay. So then we do the same for player 2. And that yields W1 is equal to W1 plus W2 squared. Now, that's already simpler. That means that W1 is equal to W2, and they're both equal to W1 is equal to W2, and they're both equal to this expression, which is basically twice W1 squared, or twice W2 squared, which is 4W1 squared. So it means that either W is equal to 0, which we know is not an equilibrium, but there is something like that. So since W1 is not 0, not an equilibrium, we can divide by that, and then we just obtain that 4W1 is equal to 1. W1 is equal to a quarter. And again, as we already know, W2 is also the same. So that's what we have found. Well, the W0, it's actually 0 exactly. So the only thing is that indeed a maximum, and I think it is a maximum because the second derivative will be, what will be the second derivative? Well, let's try making the second derivative. Taking the second derivative, just d2 q1 by dw1. Second derivative is equal to, what is that? So we just look at the sorry. Wait a second. The 4 power 4 1 plus w2 squared, and minus 1, of course, we get 0. So that is basically, what is the value of that thing? I think it should be fine. You see, I didn't even think of that. So it's w1 minus plus w2 squared minus 2w2 divided by the sum of w1 plus w2, right? And then I want to show that it's negative. When is it negative? I forgot to check this. Let's hope it works. It's negative if and only if I move that to the right, multiply by w1 plus w2, and then we get w1 plus w2 to the power of 3 is, sorry, it's strictly smaller, no, smaller than twice w2. And that is the case because in this point we are looking at w1 and w2 are equal. So w1 plus w2 is equal to let's just see. Maybe actually at w1. Well, actually, we just need to substitute that. What? Let's just forget. I'm not doing the right thing. I just need to substitute and then take a look. Substitute the point. It's not so clear. I'm used to those simple problems when it's clear that it's the right sign, but let's now just substitute W1 equal to W2 is equal to 1 2/4, 1/4, and then it's going to be equal, so half, because the sum is half, to the square minus twice is going to be half divided by the sum, which is also half. So it's going to be quarter minus 1, minus 3/4. That means that it's a local, and so global, local. Okay, and let me just. That's basically it. First of all, that's the end of our calculation, and that means that local and so also global maximum. Good. So now let's go back to what we did. So that's the only Nash equilibrium. Now, is that also competitive equilibrium? We want to show, we hope it's not, and if I have not made a mistake, it is indeed not. So it's not, because the price should be the sum of the W's divided by C. What is the sum of the W's divided by C here?
1/4 plus 1/4
Right,
divided by 1.
exactly. So it's half.
Yes.
Now, what is this? Let's show again this function in the definition of the competitive equilibrium. We have this function. So given that there is this price, now I forgot that I can actually influence it. I just want to see what is the function which I think I can influence. So that's simply the mu of W divided by, so then the function is simply piece of WR, let's say, or W, let's speak of W1, is equal to this identity function of W1 divided by the price, mu, which is half, minus W1. Agree?
Yes.
Which is twice W1 minus W1, so it's W1. And of course, the same P of W2. Now, that's not a competitive equilibrium, because then everyone would definitely profit by indefinitely increasing that thing. So that's not optimal. Everyone, let's just finish the exercise and then make a break. Everyone would strictly benefit from bidding higher. For this price, there is no competitive equilibrium. Definitely, that in particular, that's not. Now the other direction. What is a competitive equilibrium which is not Nash? So let's just find the competitive equilibrium, and it will finish it, because it cannot be Nash. We already know that the only Nash is not competitive. It's not the other direction, it's the other question. So now let's find next. Let's find a competitive equilibrium And again, I'm not sure that the functions I took are kind of good because they're kind of too simple, but it's fine. It's fine. I think that eventually it works. So let's find the competitive equilibrium. What I would eventually want, it's important to show how I thought about that so that you actually can understand this and not just see the technique for this concrete exercise. So I want this to be an equilibrium. Therefore, I need this. So in general, I want this PR, which is equal to VR of, I remind you that we call this capital UV. VU was for us utility, the value is V. That's the difference from the notation we used in the books. So VR of WR, let's talk it not VR, it's V1 of W1 is VR of W1 divided by the price minus W1. We want that. Well, that's because we know what VR is. That's the identity. It's simply W1 divided by mu minus W1. Now we want that to be optimized. Now, since it's a linear function, it can only be optimized if it's constant. It's a linear function. So it can only have, well, it can have only have, let me just write it more, have optimum if either W1 is equal to 0, and we know that's not the case, because we already saw that the W, I think somewhere, so yeah, that then is going to be 0, then we saw at some point it's not a good idea for us. I don't remember where. Let me take a look. That, yeah, because if W is if both are equal to 0, that's not a good idea. Actually, it can never be an equilibrium actually in 0, because if it's 0, let me think. If both are 0, then thought it's best for you to W1 is 0, then it's going to be W2 else who's let me see. W1 is 0, it will mean that W2 is also 0 or not. It means that the utility of course is 0. But then the W2 is not 0. If W2 is 0, I think we assume it's not 0. Then it's of course not stable because W1 can just change to what W2 does and get some positive utility. Well, on the other hand, no, but because there's a price. Okay, I think. See, I forgot, and I wanted to make it more clear, but I forgot because I first all conditions. Yeah. So W, anyways, if W, without going to details, if W is 0, if the player gets 0, it's not an equilibrium. Let's not go to the details because it will take more time than it is worth. So if W is 0, it's not an equilibrium. It's not optimal. Another option is the other extreme. No, there is no other extreme because there is no maximum. So the other option is simply that this function has a local maximum, but that means can only be a constant function. So it's a constant. In other words, W1 divided by mu minus W1 is equal to a constant. It can only be if that's 0. Because in 0, it is 0. it can only be W1 divided by mu minus W1 is equal to 0. And that means that mu has to be equal to 1. When can the price be 1? So the price can be 1 only. Well, just see, because in reality the price is dependent on those. We don't look at this when we look for competitive equilibrium, but it is in reality dependent. So the price has to be 1, and that means that okay, I'm looking for this too. Yeah, the price mu is equal to the sum of W1 plus W2 divided by the resource. Is equal to 1. The resource is 1, so the sum of W1 and W2 is equal to 1. Now I don't even think doesn't have to be equal. Let's try W1 equal to W2 equal to half. Let's try. If it's a competitive equilibrium, we are done, because then we found one. And that's actually going to be a competitive equilibrium, because then mu is going to be 1. This p function is going to be optimized because it's just all this constant. So it's a competitive equilibrium. And we know it's not Nash, because we already found that the only Nash is when they both are a quarter. And we know that it's not the only Nash equilibrium. So we are done. Do you have any questions?
No.
Okay, then let's make a break of 10 minutes and get back to the next question, where we're already going to the auction topic. Maybe, I don't know whether you do it, but maybe you can actually stop the recording for now, so that there will be no dead time on the recording.
Yes, I'll pause it now.
Thanks.
Resume
Recording in progress.
Yes. Okay, so now you hear and see everything, right?
Yes.
So let's move to the next exercise. Now, the most famous application of this ECG, is simply called the weekly auction. Concrete case for the auction is the second price auction. Let's just this exercise is simply, it's very simple. Just let's try to run this second price auction for this simple case. So you have 3 buyers with values. Their values are 1, 2, and 3. So assume they act truthfully. So who is going to bid what?
Player 1 would bid 1, 2 would bid 2, and 3 would bid 3.
Right. So let's just write it down. Let's say 3. So the values 1, 2, 3. The truthful bits, by definition of truthfulness, 1, 2, 3. So who is the winner?
Player 3.
Right. Player 3, because it means the player, right? I should write like that. The player 1, 2, 3. That's the values, that's the bit. So the winner player 3, and he pays. How much does he pay?
2.
He pays 2, exactly. He gets, so his utility is 3 minus 2. is 1. And the rest, of course, don't get anything and don't pay anything. Good. The next exercise is a bit more interesting. So at the lecture, I mentioned that the first price auction is not necessarily truthful, while the second price auction, we proved it is. Now, what I want to show now is consider auction an item to n players. You can choose, you may choose the n, you may choose everything. Just give a show, maybe by a counter example or something, at least one case, where the case price is not incentive compatible. Do it for any k from 1 to from 1 and on without 2, of course. So first price is not compatible, third price, fourth price, fifth price, and so on. Of course, we assume that when we talk about k price, we assume that there are enough players. So it's quite simple, but let's just do it. So do you have any first let's intuitively speaking, that second price, do you remember how we proved what was the intuition why it is incentive compatible, the second price?
Because if you're bidding less than your value, I mean, if your bid is in any way what is higher than the second price, you're still always getting the same utility. It's your value. Your value is independent of your bid. If your bid is greater than the next all the other bids.
Yes. So when I win, it doesn't matter how much I bid.
Exactly.
My payment doesn't depend on what I bid, only whether I win.
Yes.
And the way the only way I can win when I lose, or the other way around, that's when I, let's say, bid too much and then I don't like it. So, and there is no reason to change the outcome, because it will not help me. So I can overbid someone and win, but then I will have to pay more than my value. So you don't want to change the outcome, and given the outcome, what you pay or don't pay does not depend on your bid. Now, what happens in the first price auction? We know that what you pay does depend on your bid. So, for example, if you have two players, I just want to, not just to give you an example where you just see it and that's it, even if you understand why it's true, I want just to kind of help you with the thought of that problem 4. So for the first price auction, the value, so there, both the winner, or let's say the outcome, I think also the winner maybe is more clear. The winner and her payment depend on her bid. On her bid. Thus, we can suggest the following example. So do you have an idea, or do you have a suggestion what to suggest to show it's not incentive compatible? Something simple, of course.
I mean, if you have to bid, if you have to win, like you can just bid something that is like even less than your value, and you can still win. And
yeah, so let's look at, let's say, two players. Consider the example of two players, players 1, 2, with the values of, let's say, 1, 2. Now, if they bid truthfully, 2 can strictly improve by if both bid bi is indeed equal to the vi. So if both the bit is equal to the value, player 2 can strictly improve by bidding what? By used to be 2. Now what shall the player bid in order to improve?
Layer 1 has value 1, right? So like something marginally greater than 1.
Exactly, by bidding 1 plus half. And here, any 1 plus epsilon for epsilon which is greater than 0 but smaller than 1 will work. Anything will do. He still wins, but now pays less. What about the cave price? Here, the payment does not depend on what you bid. So what happens with the cave price? Why is not that incentive compatible? So that's an example. Okay, not incentive compatible. And they were done. Now, what about the cave price option? Where k is at least 3. Here, one's payment does depend does not, like in the second price, doesn't depend on her bid. So why is it still not incentive compatible? Let's talk about but what can happen, what can ruin incentive compatibility on the level of idea? Let me on the level of how it works.
So if a person bids less than the second highest bid, then they are going to lose, right?
Exactly. So here the lack of incentive compatibility stems from the fact that you can actually deviate from the truth and change the guy who wins profitably. Here, profitable deviations can stem from changing the winner. So let's take a concrete example. Any idea? So consider the players 1 till n for some n which is greater than k, and assume that the value vi is equal to I. So the value of player I is I. Now, if everyone bids truthfully, player n wins. And how much does she pay?
N minus k.
And pays n minus k plus 1, I think. Let's see. So if k is equal to the second price, she would pay n minus 1.
Yes. Okay. Yes.
Yes, n minus k plus 1. Now, if she beats any n plus, sorry, not she. She cannot change how much she pays, and she doesn't want to change the winner. So who should deviate? Not she. She cannot improve because she cannot change how much she pays if she wins, and she doesn't want to stop winning. So who should pay? Who should, excuse me, deviate?
If
Player.
okay.
Yeah, which player?
If the kth player deviates, the utility decreases, right? They also don't have an incentive, and they also don't lose anything, basically.
Okay, I'm a bit confused. Which player can profitably deviate?
Oh, the n minus first player.
Right. At least that works. If player n minus 1 deviates to be the following, the new bit of n minus 1 prime, let's make it any n plus epsilon for any epsilon which is greater than 0. Then what happens? Then she wins and pays. How much does she pay?
N minus 1, still
So
minus
what
k
is
plus
the... Yes, my apologies. Please continue. I interrupted.
1. She still pays k plus 1, right? Because then now her position is shifted in the bidding order.
So she still pays the previous first player is now on the second, and the other player maintain their positions. Exactly.
Yes, but her value is since it's n minus 1, she profits.
N minus k plus 1. She pays the k, right? Let's calculate. She pays n minus k plus 1. Her value is the same value, but let's now show that it actually is an increase. First, do you agree that she pays n minus k plus 1?
She pays n minus 1 minus k plus 1, right? Because her value...
No, her value has not changed. She beat something different now.
Yes, but her value was n minus 1, right?
Yes.
So her value, it should be n minus 1 minus k plus 1, right? No, that would...
no. She pays the n. That's a good... You see, it's a good exercise that it actually helps us understand it better. She pays the k minus, excuse me, the k largest bid.
Yes.
First of all, it does not matter what her value is.
Yes.
You only look at the bid. So let's take a look. Let's take a look at that. That's good that you are asking. So so before and players bid what they actually think. It was 1, 2, 3, n minus 1, n. N minus 1, n. So player n won, and she paid the kth largest bid. So the first largest bid was n. The second largest bid was... Before they bid, the bids were... The second largest bid was n minus 1. The third largest bid was n minus 2, and so on. Do you agree?
Yes. Actually, so the confusion was I was talking about the profit of the player, but you were talking about just the price. I think that was the difference. Yes.
Yeah. Okay.
I understand this.
Okay. Then, so do you agree that the
yes
payment is that good?
Yes.
And let's move to the no. It's important to talk about it's important let's just close, to talk about the price. You need to show it's a strict improvement. But I just want to go step by step. So player n minus one divide by bidding n plus epsilon for any positive epsilon. Epsilon can be huge. It doesn't matter as long as it's strictly positive. She wins. What does she pay? She pays n minus k plus one.
Yes.
And therefore, a new utility of n minus 1 is equal to her original value, which is the same, n minus 1, minus her payment, minus n minus k plus 1, and that is k. One second. That is k minus 2, right?
Yes.
And since k is at least 3, it is at least 1, which is greater than what she got before, which was 0. It's strictly greater than, which is strictly, of course, don't write it nicely, like I should not write a strictly greater within text, but it's, I think, for this for tutorial, it's fine, which is strictly greater than, okay, what she got before. What she got before, namely 0. Okay, so we have shown, I think, that it's not incentive compatible. At least there is an example. I'm not talking about a family of examples for every. I mean, for every such n and k, for every k there is an example. That's what we wanted here. Any questions?
No.
Good. Now let's talk about something we did at class. So don't worry, I'm going now to do it again, since you didn't have time, or maybe you had time actually to read that. But we need to do it again anyway. It's about one of the several examples of application of VCG was called a public project. So we need to recall that example. And then we said that it can be proven that what the players pay together is smaller than the cost, so you actually need to subsidize that. And the book says that we can also prove that it's always the case, but that's something we don't do with our course. Now, that's what we need to prove. So let's go to public project, so that unless that's the sum of the values is C, then the total payment is of the users, of the citizens, is smaller than C. But let's go just and solve that. So let's go to the lecture. So that was what we saw at the lecture. So let's go over it together. The government undertakes a project costing C, and there are n citizens. Okay, however, I think n. Each citizen values the project as some value, which can be also negative. It can be that the citizen does not like that there is a bridge somewhere or a park or something. So the government is an extra agent here, because we now see that we want to take into account the government's utility too. So that's a bit unusual. That it's not that there is this auctioneer who is outside, but actually we want to take the auctioneer's consideration into account. So the social welfare is simply the sum of the values of the agents minus the cost which is incurred, which is borne by the government. That's the social welfare. So the optimizing tells us that we need to undertake a project if and only if the total cost is at least the value taken by the value the government has to pay. Is that fine? Is that do you understand it?
Yes.
Now, what are the payments? Now let's use the Clark pivot rule that says that the government pays 0. Okay, we don't say how much the government pays in the book, but I did it as an exercise. Let's actually do it. It's nice. So do you remember what Clark pivot rule is? Maybe it's a good idea to recall that. What the Clark So I remind that mechanism the VCG is defined in general that there is some function which optimizes the sum of the utilities, and the mechanism also charges some prices. Now the prices can be okay, that's not that. My apologies. That's a requirement. Okay, the mechanism of VCG is the following mechanism. So look at what I'm showing. The chosen alternative optimizes the total social welfare. In particular, if it's like an option where one player gets something, then you just choose a player with the maximum value. But in general, when you have more complicated structure, a more complicated structure of alternative, you just choose an alternative which optimizes the total social welfare. Of course, according to what you are told, according to the reported values. And the charge that user I pays is some function, it can be any function, of what the others bid, so it does not depend on that player, minus, it does not depend on that player's bid, minus the sum of what the others, according to their reports, get from the chosen alternative. So again, the chosen alternative is an optimal alternative. That's simple, assuming that everyone bids truthfully. But the payment is first of all some function of something you don't have an influence on, minus what the others get from the alternative. Intuitively speaking, if everyone bids truthfully, then what you get, your utility, simply what you get from the alternative minus the price. So what others minus what others get from an alternative together with what you get is simply the social welfare. It's the total thing minus something which is called HI, and you want to which you don't have an influence on. So the idea is that you kind of want to optimize the social welfare. That's the intuition. But this H can be chosen in many ways, and we said that if you choose, for example, for simplicity, because it's enough for the choice of any H is enough for incentive compatibility. But if you want that also to be reasonable, you have some, because you have other requirements. If you choose H to be 0 for simplicity, to be constantly 0, that won't satisfy requirements like that the mechanism does not pay the users, and which is where they call no positive transfers, and that it's ex post individually rational. And one of the approaches which satisfies those requirements is called Clark pivot rule, which is one of the approaches. So it's a nice way to actually use the ECG. In particular, in the case of selling a single item that eventually results in the second price auction, as I showed you at the lecture. So the Clark rule is as follows: this H of the function of what the others bid is simply the maximum of what they derive from an alternative, not necessarily the alternative which has been chosen, but we just look for an alternative which would maximize what they derive. So pay attention. We first mechanism maximize the total utility according to the bits. Now this function is defined by maximizing the utility of all those besides player I. So I hope you understand. If not, let me know. It's a bit confusing. Now under this rule, then what you pay is you pay HI minus the sum of what the others get. But HI is also the sum of what the others get. Simply that HI is the optimum sum that the others can get if you only want to optimize that. And then you subtract from that the sum of what the others get when you optimize not what they get only, but you optimize the total for Shavaraka, what they get and what player I gets. So what player I pays is the difference between what the others get when you actually want to only satisfy them, minus what they actually get when you want to satisfy everyone else. And individually, that's kind of a cost that player I imposes on the others, and he has to pay that. That's the intuition. Now, and those requirements they hold, and sometimes you require that this v is not zero and all that. But anyway, that's the Clark pivot rule. Now let's apply this rule to our example. Before we do that, do you have any questions about Clark pivot rule?
Could you explain the second part, what player I is paid? I understood the first part, but the second part not so much.
You mean the one actually which is now highlighted, right?
Yes, yes.
So the general payment form is HI of V minus I minus what the others derive from this chosen alternative.
Yes.
When it has been chosen, so that the sum of everyone is optimized. Now, when we actually choose this H to be what we told, the maximum of what they can get, when you actually optimize what those guys besides I get, and then you substitute that H to this formula, H minus this sum, you get two sums of what the others get, the guys besides I. But in the first term, you get what they could have got if we only thought about their total welfare. What I'm highlighting now, whereas in the second term, which you subtract from the first one, you get what they actually get when you've been optimizing the sum of everyone, including the player I. So that's one has this alternative B, and the other one has this alternative A. A is what the actual choices based on the optimum of everyone together. B is what can be chosen if you want to optimize just the sum.
Okay.
Is it clear now?
Yes.
Okay. Now let's move to the exercise. It's a bit confusing, but the exercise, but it's so. What does this Clark pivot rule tell if we want to use it here? So what does the government pay? It's also a player here, we said. So if there are several cases, if the sum of the values of the player, of the citizens, actually, the government is a player, but is sum of the values of the citizens is greater than what the government's costs are, then what the others, we basically need to see, okay, let me maybe go back and explain something. So we need to take a look at what is the difference between what the others obtain with when you just want to satisfy them, not like without me. I'm also playing, I'm also acting, but you just think about what is the best for them and what they obtain when you also think about the best of everyone. So when the sum of the values is greater than C, it means that the project is undertaken. It means that regardless whether you think only of the best of the citizens or you also think of the government, you will build the project regardless, because the sum of the values is greater than C. So the same alternative will be chosen, and therefore the government will pay nothing because it has not imposed any utility on the players. So maybe let me write it down. So the public project So if the sum of the utilities of a class is greater than C, then when you want to optimize, so when you look at the maximum of the sum of the utilities of the class, and you don't care about the government, you want, and then you subtract from that the maximum of the sum of the utilities of the class. But when you look instead of that at what is the mechanism, what does the mechanism choose, this F, you get the same, because the total will of the players overweights the will of the government, kind of not to do anything. Do you understand? So that's going to be 0. And the same goes if this sum is smaller than 0. If players together don't want it. Also, then it will mean that in total, the players don't want to build anything. And with the government, definitely they won't want to build anything. So the chosen alternative will be the same, regardless whether you take into account this player called government. The only difference can be when the sum of the values of the players is between 0 and C, because then if you only care about the players, it's still positive, so you would build it. If you however care about the sum of them and the government, I mean what they do minus C, because C is the cost of government. C is the it's the value of the government, the negative value for the government to do something. You would not do anything. Then the government has to pay the difference. Do you understand, or do you want me to explain it again?
Could you say it again? I understand the first part, the first equation, but not the second part. If
Okay.
Vj is less than 0, then
Okay. Then the same happens. So the maximum of the values without, when you just want to optimize the well-being of the citizen, is 0, because the citizens on average don't want to be, the B will be not or don't build.
yes.
And the maximum when you do care about everyone, including the government, will definitely be don't build, because the government only adds minus C to the sum. So F will also be don't build. So it's also going to be the same, and therefore the government will have to pay nothing. It will, so the government does not incur any payment on the users. The presence of the government does not change anything. If the users wanted to do it anyway, if the users wanted to do it more than the government doesn't want to do it, or if the users don't want to do it anyway. In those cases, the presence of the government does not change what happens to the users.
Okay. Yes.
Now, in the case, the only case where it does, then it can change, and that's where this sum is exactly between C and 0, and then what the users get, if you only want to benefit the users, you don't care about anything besides the sum of the users, will be the sum of their values, something positive or non-negative. What they, however, get if you want to benefit everyone will be nothing, because then you won't do anything, because the government's cost outweighs the total value. So this is going to be sum of the values of the users of build, and maximum of the weight of this F, what our mechanism decides, is going to be 0, because the government is more lazy than the people want to build. So the government will then have to pay the sum of the values of the users. Maybe that's not what they ask even in the book, what they tell in the book, but that's that's something I just wanted to apply this Clark's Fibonacci rule so that we will exercise that. So do you understand that?
Yes.
Okay, that's again, that's just that's just a bit of a confusing thing. Now let's go back to the lecture. Now, what about the interesting thing is that the payment of the citizens? Now, citizen I pays nothing if she isn't pivotal. Now, how do we define being pivotal? That the citizens, besides that guy, don't want to build any. They don't want it enough, at least. Whereas the guy, they want it enough. So she's pivotal. She actually changes the decision. It can be that all the citizens are pivotal. For example, it can be that we two of us decide something, and each one of us wants that to the extent of 3/4, and the government doesn't want that to the extent of 1. So each one of us alone is not enough to make it done. But if you work together, it will be 3/4 plus 3/4, 1.5. It will be enough. It can be that both are pivotal. Anyway, if you are pivotal, it means that you are positive and your value actually makes it being built, or you are negative and then it's the other way around. So without you, the guys didn't want enough. Excuse me, without you, the guys wanted it more than the government was lazy, and not lazy, more than the cost of the government. Now with you, they suddenly want it not more, because you are negative. So you understand, first of all, the notion of being pivotal.
Yes.
By the way, it's similar to what I showed you above, that the government can be actually pivotal or not. So if the total V is greater than C, the government is not pivotal. You will build it anyway.
Yes.
By the way, pay attention, something confusing, that it's not like you don't need the government. The government kind of will build it according to our story. But you don't need to think about the government's value in order to build it. That's the idea.
Mm-hmm.
So if someone is not pivotal, then she does not change the outcome. And in particular, she doesn't pay anything, because what you pay is what the others get with one outcome minus what they get with another outcome. What they get when you only want to help to satisfy them, or when someone only wants to satisfy them, minus what they get if someone wants to satisfy everyone. If there is no change because of you, there is no difference in those sums. So if you're not pivotal, you don't pay anything. If you are pivotal with a positive V, what do you pay then? So what you pay is that you pay the following. With you, without you, if you have a positive pair, what does it mean to be pivotal? That's what it means. Without you, the sum of the values was not enough. So without you, that thing would not be built, and then they would all get they would all now they includes the government, by the way. So people would not get anything, the government would not pay anything. It would be 0. Now, with you, people will get something, their values basically, and the government will pay that. Because with you, the decision is to build. And the difference is C minus the sum of the values. Do you understand that?
Yes.
Good. Then if she's pivotal with a negative V, then that's what we mean. What do we have? With you, without you, if you only want to help them, it will be built, and then what they would get is that the citizens would get the value, the government would bear the costs. Now, with everyone, including you, it will not be built. So nobody will do anything. The citizens won't get the values. The government won't bear the cost. It will be zero. So that's the value which will be charged from you. And that was what we said at class. Now we also said that finally that we can show that the total payment from the citizens doesn't cover C unless the sum of the values is equal to C. So the mechanism needs to subsidize the trade. As again, we already mentioned that, I think we did mention that. Anyway, it can be shown that there are a class of cases when the mechanism needs to subsidize the trade. But anyway, we need to show that. So the question is, how can you show that the total payment from the citizens does not cover C? That's not very complicated. It's just a play with the formulas. So what is basically the total payment from the citizens? First of all, only pivotal citizens pay. Now, what do they pay? The pivotal citizens with positive values pay this. The pivotal citizens with negative values pay this. The difference basically between the cost and the sum of the values of all the others. Do you agree?
Yes.
Now let's assume for simplicity that only. Let's assume for simplicity. We are out of time. Let's assume that. For simplicity, that all the pivotal or maybe even like that only pivotal that everyone is pivotal with that only pivotal players with W greater than 0 exist. Then the total payment of the players, what is that? Now each player pays, each such pivotal player pays C minus the sum of the values. That's what we showed. Do you agree?
Yes.
The total number of such players, let's call it K, not necessarily whatever, D. So you basically, if you sum, first of all, they all pay D times C. Then they all pay minus D times the sum of everyone besides themselves. So you can basically tell that you pay the sum of everyone, D times, minus D times the sum of everyone, and then you just need to add to, because you forgot to tell that besides themselves, you just add, you add the players we were talking about. Add those players. where those are pivotal with positive value. And what is that? That is D times C minus D minus 1. So, let's assume that all the values are do this. Wait, one second. I want to say that minus D minus 1 sum of all the values, but we don't sum here all the values. Maybe but it's okay. It's going to be at least the sum of all the values. Okay, no, there can be more. Let me see, let me think. Yeah, I need to assume that everyone is pivotal, I think. Let me think whether I need to assume that. So I look at each pivotal player with a positive value pays C minus the sum of the others. So if you look at all the pivotal players together, you pay D times, so the number is D times C, minus the sum of the values of everyone, and then you need to add the sum of those guys. And then what I tell you is that it's at more. Wait a second. Because I made a mistake, a typo in my solution. That's why I'm confused now. 1 second. Sum of the V's is C. That can I think okay. I think I can. We don't need. So basically, what we basically assume here. Let's assume that only players with positive values exist. That's the assumption we do. I'm not sure. Let's see whether it works. Because now, having found a mistake in my proof, I'm now trying to do it while talking. So let's assume that all the players have positive value, positive V. In particular, all the pivotal pairs have positive V, but also we're going now to use it for something else. So for all pairs, the V is positive. Now, what we're going to use it for, the second use is we're going now to tell that this sum is going to be smaller or equal than this dc minus d times this sum. Now I'm just copying what was it before. Plus, I increase what I have by summing over all the values, not only of the pivotal, but all the values. And again, they are always positive V. Do you agree?
Yes.
Now, what I now show that even this thing which is greater than what used to be, even this thing can never be greater than C, or at least C. Or in other words, you know what? It's even okay. I think I can do it better. This thing has to always be okay. Vi, first of all, how it is equal to. So I have this d minus 1 Vi. It's going to be like d times C minus d minus 1 times the sum of Vj. And I want to show that it's enough if I prove that it's going to be at least C. That's what we proved, that the sum is at most C. Under this assumption that the values are positive, that's enough, right?
Yes.
Left to prove. Now, why is that the case? Because that is at most C if and only if move C to the left-hand side and move this thing to the right-hand side. All this thing. And then you will see d minus 1 times C is at most d minus 1 times this sum. D minus 1. And then, well, these at least, we need to assume that there are enough pivotal pairs. Wait a second. Okay, no, it's fine. That always is the case because that's okay, that's done. That's always the case because the eventual decision is to build. That's the only case we are talking about. And since we are considering sorry for the confusion, the case when it is when this F, the decision is to build all these holes. So total values are at least a C, and therefore you can multiply it by whatever you want. Even if it's 0, it still will hold.
Okay.
So okay, I hope you understand it. If you don't, if you want me to explain more, let me know, because I got confused because I found a mistake in what I had written before the lesson. My apologies. So it got kind of confused. But basically, we assume that all these are positive, and then we managed to pivotal. And then we managed to do what we needed. Now, what happens if not all these are positive? Then that's a good question. I don't remember exactly. I think that we need just to divide this to several parts. But I think that I don't want to do it now because this that mistake. If I'm going to do it now, it's going to take too much of your time, and I'm already 20 minutes over time. But I think that it was enough. We have definitely made enough progress today. So sorry for this confusion in the solution. Now what we didn't solve is, again, I wanted to solve some exercise about VCG, where I actually show that VCG, indeed, if you really do, that it indeed charges sometimes different prices per player. Not different prices per unit as it can sound, but the price per unit can differ per player. And then there is this idea that how we can do this smoothness, which you have seen in the lesson for utility maximization, and you can read it in the paper if you want, but you don't have to. That's something which the only material you have to know is what you have seen in the lecture and tutorial and homework. Then you also show why the extension theorem requirement is important. That's actually something I can show you very quickly at the paper. If you have not seen that, you may be confused, but when you do read it, you will probably understand. So when I prove something that this bound extends for a cause-correlate equilibrium, and therefore at some point inside this expectation, I need to use this assumption. And then I use the assumption on S, which can be anything. It's something which is drawn according to this distribution. It's not necessarily a pure equilibrium by itself. A pure equilibrium may not even exist. So that's where it's important to assume that this smoothness condition, which we have not talked about today eventually, but I've talked about at the lecture, that this condition is something which we have for any S. But again, I realize that now I'm not solving the exercise. I'm just trying to give you some intuition for the future because it's the last tutorial. And then I wanted to look at one example, but again, it's fine. So good. I think that we are done. Have you got any questions?
No, just about like Studienleistung.
Yes, I need to finish checking the exercises. Don't worry. I mailed this guy who makes that formal so that he won't close that thing sometime. So I just need to finish the exercise checking. This semester I'm the guy the only one who checks the exercise, so it will take me. It won't take me much time. So anyway, I'll finish the exercise checking and then I will mark it.
Okay. I shall stop the recording then.
Yeah.